puerta? Vale, ok. Buenos días, muchas gracias por venir a asistir a este seminario. Hoy nos va a hablar Beatriz Gato Rivera, que es una investigadora del Instituto de Física Fundamental del CSIC. Tras finalizar su tesis doctoral, ha estado 3 años en el MIT y también 3 años en el CERN, trabajando sobre teoría de cuerda. Ha sido también investigadora principal de 4 proyectos de investigación y en el IFF ha sido directora del Departamento de Partículas, Campos y Cosmología y la investigadora responsable del Grupo de Física Matemática. Sus intereses científicos se centran sobre todo en la física de partículas, la gravitación y la física cuántica. También participa en actividades de divulgación y ha publicado 2 libros, Antimatter en la editorial CSIC y Antimatter, una versión muy extendida del primero en inglés, en la editorial Springer. Además, en 2021 concedieron el premio de Mejor Contribución de Divulgación en las publicaciones de la Real Sociedad Española de Física por el artículo sobre la antimateria. Así que tenemos la suerte de poder escucharla hoy. Así que, bueno, Beatriz, ahora es todo tuyo.
Thank you. Well, good morning, and thank you for coming. As you know, I'm going to talk about dark matter, dark energy, and antimatter. I'm going to give an overview, in fact, a very didactic overview. And for me, these are the exotic and mysterious side of the universe. I will explain first what are they, which are the main features. Then we will see the composition of the universe according to the cosmological standard model that is called lambda CDM, where lambda stands for cosmological constant and CDM for cold dark matter. After that, I will go into details in the dark matter, then for dark energy, the same, and from point 5 until the end, I will focus on antimatter exclusively. Well, if we had to say in a few words what are dark matter, dark energy, and antimatter, we could say the following. Dark matter is a hypothesis, is an invisible matter proposed in order to explain the gravitational fields of an unknown origin that abound in the universe. It dominates the total matter in the universe, contributing 85%, and also contributes like 27% to its energy density. Dark energy is a name, is the name given to the unknown cause that produces the acceleration of the expansion of the universe. That the universe expands, this is known for almost 100 years. But most of us, most scientists, believed that this expansion was breaking down, was slowing down. And so it came as a big surprise that in 1998 was discovered that it's not the case, but the expansion is instead accelerating the expansion of the universe. In addition, this dark energy dominates the energy density of the universe with a contribution of 68%. Finally, antimatter can be regarded as the reverse of ordinary matter and annihilates with it. It was discovered in 1932. Its contribution to the total matter of the universe and energy density is very, very small. Is amazingly small, less than 0.0001%. The contributions of the components of the universe to the total matter and to the energy density, according to the lambda CDM model, is as follows, as you can see in these graphs. In green is the dark matter, the contributions of the dark matter. In red, the contributions of the dark energy. Now, in yellow are the contributions of the ordinary matter. So it is like 5% only contributes to the energy density of the universe, and to the total matter contributes like 15%. And it's split in two colors because the purple color is the little portion of luminous matter, that is stars and galaxies. The rest of ordinary matter is gas and dust, enormous clouds that do not emit invisible light but in other frequencies, like radio waves, X-rays, etc. Well, as I said, in the universe appears to be much more matter than what is observed, judging from the gravitational fields that are detected. That is, we detect much stronger gravitational fields than the ones produced by the objects that are seen. These objects are star galaxies, clouds of gas and dust, etc. This matter is transparent and colorless, so invisible to all respects. Now, invisible and seeing matter has been proposed several times for different purposes. Probably the first scientist who noticed that it was a missing matter was Lord Kelvin, that in the late 19th century, he was making estimations of the mass of the Milky Way. The Milky Way at that time was the whole universe, of course. And he noticed that the mass that he was getting in his computations was far larger than the sum of all the stars that could be seen. So what he thought, and he wrote it, that it's very likely that the vast majority of the stars are now dead. They have extinguished. And for this reason, they don't shine anymore. Then in 20th century, there were a couple of astronomers that already noticed some missing matter, but the most prominent was Fritz Zwicky, who in 1933 proposed that an invisible matter should exist, that he called dark matter, in German, to explain the high velocities of galaxies in galaxy clusters. He noticed that with such velocities, the galaxies should leave the cluster, so the cluster shouldn't exist with such velocities. So it must exist, he thought, an invisible matter that maintain these galaxies inside the cluster. Well, the colleagues of Zwicky didn't pay attention to this at all, but more than 40 years later, Vera Rubin and Ken Ford in 1975 proposed again the existence of dark matter to explain the high rotational velocities of peripheral stars in spiral galaxies. Same story. In the peripheral stars in spiral galaxies were moving too fast around the galaxy, and they were thinking they should leave the galaxies. So this means that in the spiral galaxy should be much more matter than what is seen. And finally, there are also, let's say, invisible gravitational lenses. As you know, gravitation also attracts light, and therefore, since the light rays are bent by gravity, gravity produces gravitational lenses, is what is called, the name. So again, in many examples where there are these effects of gravitational lensing, doing the computations, one can see that the matter that is visible, that in principle is the responsible for these effects, for the curvature, these curvatures of light, this matter is not enough. It's necessary much more matter to produce such curvatures of the light. So here are dark matter heroes, Fritz Zwicky on the left and Vera Rubin. Well, this is our Milky Way as the way it looks from the outside. It's a spiral galaxy, and barred, has the center is a bit barred. This is one rotation curve, like the ones studied by Vera Rubin. This is one of them. So in the horizontal is the distance of the stars to the center of the galaxy, and in vertical, the velocity. And so you can see the dashed gray line below is the line that should follow the stars by Newtonian law, the gravitation. But however, the stars follow the upper line, the one with the yellow spots and the blue spots. The yellow are for starlight, and the blue from the line of hydrogen, the 21 centimeters line. And it turns out that these anomalous, let's say, movements or rotation curves can be perfectly explained, assuming that there are huge spherical halos of invisible matter around these galaxies, like in this image, where this huge halo is depicted in green. Here is a picture of the galaxy cluster Abel 360 when it was 5,000 million light years away. Well, it's a very good image because it shows very clearly the effects of the bending of the light due to gravitation. In principle, the lens is this cluster, but it turns out that, again, if one looks at all these deformations, so you can see all these deformed images of galaxies, in fact, these galaxies that are behind, of course, behind the cluster, and because of the gravitational lens, they come in the front. But studying this deformation, this is not possible that this cluster produces so much deformation, so it should be much more matter than. Well, the case for dark matter also includes anisotropies of the cosmic microwave background radiation, in particular the second and third peaks of the CMB angular power spectrum. Also structure formation, because the claim is that in the beginning of the universe, the effects of dark matter were crucial and gave rise to the density perturbations of atomic matter that ultimately led to the structure formation that we see today. Galaxy cluster, etc. Also, the bullet cluster, it was discovered a decade ago. So it's a merger of two clusters of galaxies, suggests that the existence of dark matter is separated from the bulk atomic matter as a result of the collision. So this is the full sky map of the CMB, as probably all of you know. And this is the corresponding angular power spectrum. And these peaks, you can see the first peak, very high, has to do with the curvature of the universe. And it shows that it's flat, the curvature in 3 dimensions. So it's especially almost flat, our universe. The second and the third peaks have to do with matter, the total matter and the baryonic matter. Baryonic is atomic matter. And also comparing both is where one gets the conclusion that should exist dark matter. And this is the bullet cluster, where in pink are the atomic matter, and in blue there are clouds that represent the dark matter, calculated from gravitational lens effects, of course, because the dark matter, as I say, is invisible. About the candidates, well, first of all, neutrinos are part of the dark matter, but very small part, like 2%. And also, some astronomical bodies, small, with very weak radiation, planet, brown dwarfs, etc., is also part of the dark matter. It's called the baryonic dark matter, in fact. So the mystery is what makes up more than 90% of the dark matter. Well, many candidates have been considered, like hypothetical particles postulated to exist in particle physics. And the most popular are neutralinos and axions in this respect. Also, could be Bose-Einstein condensates, normally of scalar particles, and primordial black holes. This hypothesis is very famous, it's very popular in the last 3 years or so. Primordial black holes were created in principle, because it's it's a hypothesis also. In principle, at the starting of the universe, much before the atoms were created. There are also many proposals that general relativity is not a good theory of gravitation at large distances, and therefore the calculations are incorrect. And well, you are doing incorrect calculations, but you cannot deduce anything, no? Therefore, you cannot deduce that it's necessary dark matter and anything. Surprisingly, dark matter could even be matter from other universes separated from ours along a fourth dimension of space. Here is. You see, in horizontal and extra space dimension, and in vertical would be universes, three-dimensional universes separated from each other. So the idea is that the matter in each universe would be confined in 3 dimensions, but gravity could also propagate through the 4th dimension, so that in each universe, scientists would detect gravitational fields from nearby universes. And well, this is what we detect. We detect gravitational fields, so it could be from other universes. Now, experiment hunting for dark matter particles are going on now for more than 40 years. For dark matter particles, I'm saying, with the hypothesis that they are particles. More than 40 years already, and not a single particle has been found. Okay? These experiments can be classified in, well, in direct search experiments, well, detection of nuclear recoils from the collisions of these particles against atomic nuclei of matter. Indirect search detection that would be to detect byproducts of annihilation or decay of dark matter particles. Also, creation of dark matter particles in the high energy collisions, in the same way that all other particles are created. Also, conversion of axions into photons. This is done using strong inhomogeneous magnetic fields. Again, axions are hypothetical. Now we turn to the dark energy. As I said, in 1998, it was discovered that the universe is expanding in an accelerated way. Now, it turns out that they could also determine that this is happening for about 5,000 million years. And remember that the age of the universe is 13,800 million years. Well, these results were deduced by 2 research groups independently from observations of supernovae of type 1a in distant galaxies. These supernovae are thermonuclear explosions of white dwarfs. Well, after this, the paradox about the age of the universe was finally settled, since without the accelerated expansion, the age of the universe would be below 12,000 million years. In other words, the universe would be much younger than the oldest stars. With the acceleration, then the age of the universe is quite bigger, and so the paradox is finished. Now, some years later, also, the analysis of the baryon acoustic oscillations, BAO, in the early universe also confirmed the need for dark energy. These are the leaders of the 2 groups that discovered the acceleration of the universe. Sol Perlmutter, on the left, from Berkeley, and Brian Smith and Adam Rees from Harvard. And our colleague Pilar Ruiz Lapuente belonged to the team of Sol Perlmutter. So she is co-author, also co-discoverer of the acceleration of the expansion of the universe. Well, the anisotropies of the CMB radiation provide further evidence for the need of dark energy because of the first peak, as I said before, shows the universe is flat. And for this, it's necessary more components in the universe that only matter. So with the dark energy, now it's perfect. Now appears that the universe is flat as it should be according to the CMB. Now, due to this acceleration, most galaxies that we see today with our telescopes are moving away from our Milky Way at speeds faster than faster than the speed of light. Therefore, the light they are emitting today will never reach us, unless the acceleration is somehow halted. Some of you may be puzzled when you hear about velocities faster than the speed of light. Well, the speed of light is only the limit when one travels through a space, from one point to another, through a space. What happens with the expansion of the universe is that the galaxies, in fact, they travel at very low speeds through a space. It's the space that expands, that inflates, carrying the galaxies along. And for this effect, there is no limit for the velocity that the galaxies can acquire with respect to each other, no limit. In fact, some galaxies that now the James Webb telescope, some are like 3 times the speed of light now, at this moment, should be, at the moment, like 3 times the speed of light, recessing from ours. Well, about the nature of dark energy, the most accepted explanation until now is that it was the cosmological constant, lambda, which appears in the Einstein equations. In general, the Einstein or general relativity. Well, and they correspond to the energy of the vacuum. The vacuum is where there are no atoms and no particles, although vacuum is full of quantum fields. Now, if dark energy turns out to be lambda, this will be a very unfortunate scenario for scientists of the future and for the particle physicists of today. For scientists of the future, because if dark energy is lambda, there is no way to stop the acceleration, and therefore, in the future, it will occur that the observers in every galaxy will only see their own galaxy, nothing else, and therefore, they will be incapable to discover the expansion of the universe and the Big Bang. And why is it unfortunate for the particle physicists of today? Because there is an enormous discrepancy between this lambda and the one predicted by particle physics, by the breaking of symmetries and things. So it would be better for us if there is some kind of unknown mechanism, like asymmetry or something, that makes lambda exactly equal to 0. Would be better. Fortunately, it seems that the dark energy is not lambda. This is very recent. This has started at the end of last year, and in this year is there are many articles in this year. And this month, in April 24, the DESI collaboration, DESI Dark Energy Spectroscopy Instrument, they do observations of baryon acoustic oscillations. They have done several press conferences explaining the results. And they really lambda as dark energy is very disfavored. And the same happens with observations of type 1a supernovae from other groups like Pantheon, Union 3, and DES. They also, what they found is that the lambda, the cosmological constant, is disfavored. But all of them need more statistics. So still it's not conclusion, but the conclusion will be very soon, in very few years will be the conclusions. And our colleague, Pilar Ruiz Lapuente, is in Union 3, is in that group, again with Sol Perlmutter. Now we come to antimatter. Why can we consider it the reverse of matter? Well, because particles and their antiparticles have opposite properties, although they also have some identical ones. So a particle and its antiparticle have the same mass, spin, and half-life, but they have opposite values of electric charge, strong charge, weak charge, baryonic number, and leptonic number. Some facts about antiparticles is that all particles have antiparticles, although some of them are their own antiparticles. This happens with the photons, the Higgs boson, and another boson. Now, matter-antimatter annihilation is the most energetic process in the universe. 1 gram of antimatter upon contact with matter would produce an explosion more than twice as powerful as the Hiroshima atomic bomb. Now, if the encounter between a particle and its antiparticle occurs at low energies, the annihilation produces only photons, which are massless. But if they collide at high energies, the annihilation gives rise to the production of other particles with mass, as well as photons, as is the general rule in high-energy collisions between particles. Why this happens? Well, this is due to two effects: the conversion between mass and energy given by the famous equation E equal mc squared. So energy equal mass times the velocity, speed of light squared. And also the fact that elementary particles are excitations of quantum fields, which fill the entire space, the entire universe. So to create a particle, you only need to give energy to enough amount of energy to the corresponding quantum field. There is a different quantum field for each particle species, although a particle and its antiparticle share the same field. And therefore, the processes between particles, between elementary particles, can be seen consist of energy and momentum transfers between the corresponding quantum fields. This is a photograph of an annihilation of an antiproton against a neon atom. This is an experiment done at CERN in 1984. And I want to show you that there are, at view, there are already 3 antiparticles. The p bar that enters, you see a p with a bar on top. This is an antiproton that enters and collides with an atom and then start the production, because it comes with a lot of energy, start the production of particles. And you can see a muon. I'm sorry I cannot get up, I cannot look up because of a medical problem. I cannot look at the screen. So you can see the mu plus that starts spiraling, and then the case is converted into anti-electron, E+. So you can see 3 of them in this picture. About the discovery of antimatter, well, it's very interesting. In 1931, Carl Anderson was investigating cascades of cosmic rays radiation in his laboratory. And then he started making photographs of tracks of anti-electrons in his cloud chamber. But he was not able to demonstrate this discovery until 1 year later, until August 32. And he called them, these particles, he called them positrons of positive electrons. See, electrons with positive charge. Curiously, anti-electrons had been postulated by Paul Dirac from Cambridge University also in 1931 in order to interpret the negative energy solution of his famous equation. His famous equation that was published 3 years before. And this equation describes how electrons behave when moving at relativistic velocities. Well, in the following years, muons and pions and their antiparticles were also discovered in cosmic rays cascades. But the antiproton, the most searched for antiparticle, took 22 years to be discovered and had to be produced in an accelerator that was constructed with this end, in addition, the Bevatron at Berkeley in 1955. So immediately after the accelerator was constructed, the antiproton appeared by colliding protons against a target of copper, a copper target. So 1 year later, since they already have antiprotons, the antineutron was also produced in the accelerator, in the Bevatron, by doing proton-antiproton collisions. Here are Carl Anderson, is upper, Paul Dirac down, and the track of the positron. This is the 2nd of August, 1932. This discovery marked the birth of particle physics as an independent discipline from nuclear physics. The discovery of antimatter was a complete revolution. Well, there are 3 sources of antimatter accessible to us: cosmic rays cascades in the atmosphere, collisions in particle accelerators, and also some radioactive substances which emit anti-electrons, so positrons, such as the sodium-22, that is artificial isotope, and potassium-40, that is a natural isotope. And for the emission of anti-electrons by the potassium-40 is the reason why bananas emit 15 positrons every 24 hours. So bananas are emitting antimatter. And also the walls, and many things are emitting antimatter around us. Well, there are many less accessible sources, well, or completely inaccessible sources for us. For example, the nuclear ovens inside the stars. Inside the star, the nuclear reactions that produce from protons produce helium. They produce enormous amounts of anti-electrons, but this immediately annihilates with the electrons of the plasma. So what comes out of the stars is not the antimatter, it's the photons of the annihilation, matter-antimatter. It is estimated that 10% of the sun's light comes from the electron-positron annihilation within the sun. And well, there are many highly energetic astrophysical processes that create and liberate lots of antimatter and liberate them to the space. Like in the vicinity of very massive black holes, it's created lots of antimatter, and also in the vicinity of pulsars also. Pulsars are neutron stars that emit jets of electromagnetic radiation. Here is a sketch of a cosmic ray cascade. Well, these cascades form when a particle from outer space comes into atmosphere and collides with a molecule, and then start the reaction. So some particles are formed, like the pions, that immediately decay, giving rise to another particles. Some of these also decay, some not. And well, at the end, if the primary cosmic ray is very energetic, these cascades can have thousands of millions of particles, can be enormous. And in these cascades, more or less half are particles and the other half are antiparticles. And this always happens with the collisions between particles, are created more or less in equal amounts, particles and antiparticles. And from the particles that reach the ground, one has to say that the most energetic muons and anti-muons can penetrate the ground, even kilometers. So they enter in our buildings, in our houses, the muons, and in our cells. And as to neutrinos, they not only penetrate, they traverse the whole Earth without noticing. No problem for them. This is an illustration of how the primary rays produce the cascades. And this is a cascade over the Pierre Auger Observatory, that is the most important observatory of cosmic rays in the world. It's in Argentina. In fact, the picture is true. What is not true is the cascade, but the picture behind is, so it's wonderful. Well, the vast majority of cosmic rays, primary cosmic, are not made of antimatter. 98% are protons and alpha particles. So a very small amount of them are antimatter, and only in the form of anti-electrons and antiprotons, only. So in the space, one cannot find nothing except anti-electrons, nothing, I mean, of antimatter, is what I mean. Or so far, our scientists haven't found anything so far except anti-electrons and antiprotons. Well, cosmic rays can reach energies much higher than the energies obtained in particle accelerators. This is very interesting. And cosmic rays are also studied and analyzed in outer space. by means of detectors aboard satellites, balloons, and even installed at the International Space Station, like the AMS detector that is operating in the station, space station, since 2011, and searches with special interest anti-nuclear, nucleus of anti-atoms, such as anti-alpha or larger particles, better larger particles, because if anti-nuclear are discovered, bigger, at least bigger than anti-alpha, some people, they say even anti-alpha, this would be the proof that anti-stars exist, because this nucleus can only be formed inside the stars. So this would be a proof of the existence of anti-stars. So here we see the alpha magnetic spectrometer is called in the space station. The detector in space that has obtained very interesting result was Pamela, that now is not operating anymore. It was aboard the Russian satellite Resus de Cayuno. And it discovered in 2011 an antiproton subbelt in the inner Van Allen radiation belt. You know, these belts are created by the magnetic field of Earth, because they trap particles that have electric charge. They trap them, and they create these belts. This is a picture of the complex of accelerators at the Fermi National Laboratory, Fermilab. And it's to show you the Tevatron is the ring, the big ring that you see in the background. It was the ring of the Tevatron. That was the world's most powerful accelerator for many years, the Tevatron, and collided protons against antiprotons. This is not at all the rule in the particle accelerators. Normally, it's not like this. They collide protons against protons, like at CERN or other things. But so this was very interesting, and they had a very important antiproton factory then in Fermilab to supply antiprotons to the Tevatron. Now let us say a few words about the matter-antimatter asymmetry. As you know, our universe began its existence about 13,800 million years ago from the Big Bang. Then, very soon after that, matter and antimatter particles should have been created in equal amounts. And right after that, they should have been annihilated against each other, although not completely, as our models know. It shouldn't be completely. And why should have been annihilated almost completely? Because the universe was very dense, small, and hot, so they couldn't escape very much from each other, let's say. Well, the fact is that after the great annihilation, proton-antiproton, PP bar, that was 1 second after the Big Bang, for every primordial proton that survived, thousands of millions were extinguished, along with the same number of antiprotons, of course. That proton that survived was immersed in a bath of thousands of millions of photons produced in the annihilation. And these photons, 380,000 years later, gave rise to the cosmic microwave background radiation, to the CMB that we observe today. These 380,000 years after the Big Bang is when the plasma that was at this moment of protons, electrons, etc., finally could stop, and the protons could bound electrons. So atoms could form. So it's what I said, that plasma finished. It was the particles of the plasmas were converted into atoms, hydrogen atoms, mainly, and some helium also. Well, it is likely that the primordial antimatter disappeared almost totally during the Great Annihilation. But we don't know for sure, of course. And the existing antimatter probably is secondary, so produced in radioactive processes, in particle collision, and in very energetic astrophysical processes. However, The problem of matter-antimatter asymmetry is not why antimatter disappear or if antimatter completely disappear, the primordial antimatter. This is not the problem. The problem is why there is so much ordinary matter. This is what is not understood at all. Why there is so much ordinary matter in the universe. Of course, you can always say compared to antimatter. Yeah, but antimatter could be zero, it's no problem. In fact, the standard model of particle physics predicts that during the primordial expansion of the universe, the processes among particles generated a surplus of particles over antiparticles. Why? Because particles and their antiparticles do not always behave identically. This was discovered in 1964. It was a shock in the community of particle physics. And it's called violation of the CP symmetry. CP is charge parity symmetry. Until then, it was believed that particles and their antiparticles behave the same. Well, but the fact is that this surplus produced because of the CP violation, let's say, this surplus couldn't have produced the large amounts of matter observed in the universe today, but a much, much smaller amount. So for this reason, the problem of the asymmetry, matter-antimatter, is a very, very important problem in particle physics and in cosmology. Now the question, if they can exist, anti-stars and anti-galaxies, well, in 1933, in his Nobel Prize speech, Dirac already pointed out that stars could not be distinguished from anti-stars judging by the light they emit. It's the same. They would look the same. He even dared to suggest that half of the stars we see might be anti-stars. In fact, stars and anti-stars can be distinguished by the emission of neutrinos versus anti-neutrinos, but this was not known at that time, and is currently beyond our reach. We cannot distinguish if a star emits neutrinos or anti-neutrinos. Not possible nowadays. But in any case, today we know that the dominance of matter over antimatter is overwhelming, based on astronomical observations of the diffuse gamma ray background, the DGRB, and the cosmic microwave background, CMB. In both cases, they do not encounter any borderlines of matter-antimatter annihilation between regions of matter and regions of antimatter. Furthermore, the detection of primary cosmic rays suggests the same conclusion. As I told you, they only see in the space anti-electrons and anti-protons, so no nuclei of anti-atoms. Well, if you see on the left is the result of what happens in a star of matter, the nuclear reactions that starting with 4 protons, and after 3 steps, one gets a helium atom that remains inside the star, the helium-4, plus photons, loss of photons, and neutrinos that leave the star. Although neutrinos leave the star very fast, photons can take thousands and thousands and hundreds of thousands of years to arrive to the surface of the star. Okay, on the right you see the same thing, but imagine a star of antimatter. So this would start with 4 antiprotons that after 3 steps would create an anti-helium atom, and will release lots of photons plus anti-neutrinos. So, as you see, the stars and anti-stars can be distinguished for that, for their release of neutrinos versus anti-neutrinos. Well, the current situation is that it cannot be totally ruled out that a very small amount of primordial antimatter has survived. Perhaps 1 antiproton for every million protons or less, as predicted by some theoretical models proposed by various research groups. This proposal is already for many decades. So there always are groups working on this hypothesis that there is primordial antimatter still. Well, as a consequence, one cannot exclude the possibility that anti-stars and even anti-galaxies exist in small quantities and sufficiently isolated from matter. But in that case, antimatter would also produce anti-planets, anti-minerals, etc., and anti-living beings, of course. Unadvanced civilizations of anti-humanoids could not visit us, of course, but we could communicate by exchanging electromagnetic waves, light, radio, video signals. No? And well, and we could also have less friendly interaction throwing stones at each other, because nothing is not a more powerful weapon than a piece of antimatter on matter, and the other way around. Well, I just want to show you one article of a very prominent astrophysicist and cosmologist, Joseph Sill, and his collaborators in 2019, while they were discussing some candidates to anti-helium from the result discovered in the AMS, in the space. And well, they considered the possibility that the events originate from antimatter-dominated regions in the form of anti-gas, clouds, or anti-stars. And they even suggest that part of the unidentified sources in the Fermi Telescope third source catalog could originate from anti-clouds or anti-stars. So now let's see a few words about the experiments with antimatter atoms. Well, anti-atoms, of course, are atoms consisting of antiprotons and antineutrons in the nucleus and anti-electrons in the shell. And antiprotons and antineutrons are composed of antiquarks, of course. Now, the simplest atom is hydrogen. Therefore, the simplest anti-atom is anti-hydrogen, with a single antiproton in the nucleus and an anti-electron in the shell. Now, this is very important. We don't know if anti-atoms exist in nature, in the universe. We don't know. We only know the anti-atoms of anti-hydrogen and no others that have been created at CERN. They have been created at the so-called antimatter factory. Well, now it's really called like this. And they were created, a few of them also in Fermilab, but very few. Joined by a new one, G-bar, and a new decelerator, Elena, that is coupled to the other one. Well, the experiments they can classify mainly in two. Spectroscopy experiments with laser or microwaves to check whether the energy levels of the anti-hydrogen atoms are identical to the ones of the hydrogen atoms. And for the time being, all results seem to confirm that the energy levels of the H atoms and H-bar anti-atoms, are identical. And there are many of these experiments, spectroscopy, there are lots of them, and they confirm that they are identical. And there are also gravitational experiments going on for a while to find out whether the anti-hydrogen atoms fall in the field of Earth with the same acceleration as matter. No? Well, so far, even though they are already for more than 10 years doing experiments, so far only they have succeeded in proving that the anti-hydrogen atoms fall instead of rise up. You say, well, what do you mean that they fall? Yes, because there were some scientists, although most of us not, that suggested that perhaps antimatter would feel repulsion, gravitational repulsion, with normal matter, and therefore they would rise instead of fall. But well, after many years, they finally have found that they fall also. Now they have to find if the acceleration is the same than with normal matter. And this picture, you can see the annihilation of anti-hydrogen atoms with the walls of the traps. The traps, in this case, of the alpha experiment. They are inside the traps, and even if they are inside the traps, some of them collide against the walls, touch the walls, and of course annihilate. But sometimes they release the traps, for example, to see if they fall. Because if they are trapped in a magnetic field, they are trapped in magnetic field, you cannot see if they fall or not because they are trapped. So they have to release, and then they can see if they fall. And well, all these bright lights are the annihilation, so the anti-atoms in this case. Well, finally, we are going to see a few words about medical and technological applications of antimatter. Well, the annihilation of positrons, that is anti-electrons, with electrons from biological matter provides one of the most important imaging techniques used in hospitals. This is the positron emission tomography, PET, no? PET, in which drugs, medicines containing radioactive isotopes that emit positrons are injected into the body of the patient. Well, when the positrons are annihilated with electrons from the surrounding tissue, two gamma rays of 511,000 eV are emitted in opposite directions. These photons are detected by the tomograph, the apparatus, which produces a series of slices across the body that combine to form a three-dimensional image. Well, PET scanners can follow biological processes such as metabolism, blood flow, neuronal transmission, and tumor growth. And for these reasons, these techniques are very well suited for investigating the brain structure and activity, and for making 3D image of tumors also. They are also used in pharmaceutical industry to study the behavior of medicines in the body because of the following of the metabolism. This is well, an image of the apparatus, the tomograph, with a patient that is entering inside. And these are slices. These are from a hospital, in fact, from Kansas. Slices, PET images indicating dementia, apparently. Well, the radiation with positron and anti-muons also is of great use in material science and technology, for example, to study semiconductors, used in solar planets and other electronic devices, well also as study other materials with important technological properties, such as ferroelectricity, superconductivity, and magnetoresistance. The radiation with positrons and anti-muons is also used for many, many other applications. For example, here I have put a few, to obtain images from the interior of some materials. For example, to analyze nuclear waste that is inside, is enclosed inside a material. Or to see also the flow of oil inside machines and engines. Also is used to prove sub-nanometric scales in biopolymers. This is of interest in medical pharmaceutical industry to make very small medicines. Also to find structural defects in crystals and other materials. Well, now it's a very important question. It comes a very important question. Could we use matter-antimatter annihilation as a source of energy to cover the daily life needs of our society in the same way as we do with nuclear energy? And the answer is no. With today's technology, it's not possible to produce these amounts. We can only produce ridiculously small amounts of antimatter, and at the cost of a huge effort, both energetically and financially. For example, the annihilation of all the antiprotons produced in 1 year at CERN, that is 10 to the 13, would supply only enough energy to keep lit a 100 watts light bulb for 30 seconds. And on the other hand, to produce a single gram of antiprotons at CERN using its current technology would take 60,000 to 100 million years, so more than 4 times the age of the universe. So the situation is quite bad, as you see. Okay, thanks for your attention. And you have any questions, of course you can ask.